So this lesson is on motor circuit overcurrent protection, and we've been talking about how to calculate and how to determine the overcurrent protection, but we should probably talk just a second or two about what we're going to use for overcurrent protection. So overcurrent protection, we're going to use I'm going to draw one and then I'm going to label it. We're going to use a fuse. And typically that fuse is going to be a dual element, so it means there's actually two elements inside there. And one of them provides overcurrent protection, and the other one actually acts as a bit of an overload device as well. So that's a fuse. A second item we can do is we would do a circuit breaker, and of course we're going to have on, we're going to have off. So the circuit breaker, it also accomplishes this goal. There's some disadvantages to a circuit breaker, but of course there's also some advantages to the circuit breaker in that we can reset. So circuit breakers can reset. Fuses, once they blow, they have to get taken out and replaced and cannot be reset. So Article 430.51 is going to talk about overcurrent protection, and what Article 430.51 tells us is that each motor shall have a device that protects it from both fault currents, and remember, fault currents are short circuits, so somehow the path that the electrons are supposed to flow, somehow those came in contact with each other. The electrons are making that short cut, and in that case, if we're using a fuse, we're going to see our element is going to burn, and so we won't have continuity any longer in the center of that fuse, and that will turn off that motor circuit. We've also spent a little bit of time looking at overloads, and we'll talk more about overloads here in the next slide. But remember, overloads are usually part of, in a three-phase situation, we're going to see that as this bottom portion down here, the overload section of the motor starter. So we've got a starter, and this bottom section here is our overload portion, of course. So here's the section 430.51, motor branch circuit, short circuit, and ground fault protection. 51 tells us kind of the general characteristics and the specifics, and then 430.52, that gets into more of the rating or setting for individual motor circuits. And then we're going to spend some time looking at this table here, table 430.52, and that's the table we're going to use in order to apply a percentage rating to the motor current rating that we would find in Article 430.250 or .248. So a couple more notes here to talk about. A fault, of course, is current is a short circuit, and we need to have current protection will be provided by two types. So in the event we have a fault, or in the event we have a short circuit, and we develop too much current in that motor circuit, we have to have one of two ways to protect that motor circuit. We're going to use a circuit breaker, which we looked at earlier, and it has to be capable of sensing faults and disconnecting all the phase conductors at the same time. Now that circuit breaker, because of the fact that it's a motor, it's going to struggle just a little bit, because when a motor energizes, the current goes quite high initially, and then that current begins to come down, and once that motor is running, that current is going to be basically a flat line, pretty consistent throughout the period of time that motor is running. Well, when you're using a circuit breaker, they are not big fans of this right here, where the current goes up at a fairly high rate, and it goes up in a very short amount of time. So this bottom represents time, and this represents more current going vertically. So circuit breakers don't like that. So ideally, a fuse is going to be kind of our first choice, because fuses handle this situation much better than circuit breakers do. And when we actually calculate some of these, you'll see one of the big advantages to using the fuses. So here's our percentage table we're going to use, table 43052, maximum rating or setting of motor branch circuit, short circuit, and ground fault protective device. We have to first find the type of motor, so that's this section here to the left, and it gives us all of our options. Most of the time we're probably going to be looking here in single phase motors, or we're going to be looking in AC polyphase motors other than wound rotor. Those are kind of the most popular choices, but if you kind of notice, most of the numbers here don't vary a whole lot based on where you're looking. So there's kind of quite a few of them that repeat. These energy efficient ones, obviously there's some differences, but most of them are pretty much the same. So what these columns tell us is that in the event, or what we're going to do is, once we determine our current rating of our motor, so we go to say 430.250, and we get that current rating of our motor, let's say it's 12 amps. What we're going to do is we're going to multiply that 12 amps times, in the case of us using a dual element time delay fuse, we're going to multiply that by 1.75. And once we go ahead and calculate that, then we will. So once we calculate that, we're going to get a value of 21. So our fuse has to match 21 value. So that's our fuse size. However, you guys hopefully remember, we don't have fuses in kind of oddball sizes such as that. So what we're going to have to do is round that up. So we're probably going to be looking at a fuse of 25 amps is going to be our fuse that we're going to shoot for. Now the question is, could we say, in this case, round down and use a 20? Yeah, we maybe could, and that would be, acceptable, but in the case when the motor begins to work a little harder, we may see that 25 amps, so it might make more sense to do the 25 amps. This one's kind of one of those tricky ones where we as electricians sometimes have to kind of use our judgment and make a choice as to which direction we're going to go. But that's the process. So we apply this multiplier, this percentage, times whatever the value, the ampacity value of our motor is, which we locate in 430.250 for three-phase motors, or 430.248 for single-phase motors. As far as overload protection, we've been spending a lot of time with that. Remember, overload protection, we're going to use one of these items up here. Most of the time, if that's a three-phase motor, it's going to be either a magnetic overload or some type of eutectic alloy overload. And then we talked about the bimetallic thermal discs for single-phase motors. A table saw, or sometimes, we talked about your buddy's air compressor or your dad's air compressor. So those are going to be single-phase motors. They're going to have those small little red reset buttons, which is integral or built into the motor. So here's our code section that talks about the thermal protector being integral or built in, and gives us some parameters. Obviously we're not going to be building those electric motors, so obviously the manufacturers have to design and build theirs to meet those specifications. We're just making sure that they are going to meet those specifications. One thing to keep in mind for three-phase overload units, I've got 3 legs of them drawn here. So we've got a black phase, a red phase, and a blue phase. We're looking at one of these 3 voltages as kind of possibility as far as three-phase voltage. So anytime we're doing a three-phase motor, any three-phase voltage system, 3 overload units are going to be used, and 1 is going to be placed in each phase. So 1, 2, 3 units, 1 in each phase. And again, most of the time we're dealing with equipment that's made by a manufacturer. They obviously understand how they have to manufacture that equipment, and so they're going to follow the guidelines of the NEC to make that equipment function the way the NEC demands. And you're going to see it set up where if a 3-phase motor starter is going to start a 3-phase motor, you're going to use 3 overloads, and 1 of them is going to be in each phase.